All right, good morning or good afternoon and welcome to our next lesson. We are starting topic D today. Topic D is all about systems of linear equations. And just a forewarning, these lessons are going to be pretty difficult to begin with, but they will ease up once we get used to it. Just like with everything, it takes practice and time, okay? So we're going to continue with our standards EE5 and EE6 today. And the reason for that is I'm going to try to break up this first lesson, lesson 24, into two parts for you. So we're really just going to focus on the parts that we've already known and been learning and adding an extra step into it today before we move into our really new stuff tomorrow. So by the end of this lesson, you'll be able to determine how real-life situational changes can affect our linear equations. So we're going to be working with a bunch of real-world scenarios today. You'll know you're successful when you can create two linear equations from a real-life situation and then use the situational changes to manipulate and change your equations accordingly. So for example, you're going to get stuff like this. If I run 5 miles in 45 minutes, but I stop for 5 minutes to take a break, how would my equation change? What was that extra 5 minutes being stopped? How's that going to change my math? So that's what we're learning today, and that's what we're practicing today. As always, I'm going to start off with some reviewing of background, and you'll watch me do that. We'll do some examples. You'll do exercises together and on your own. We will close out the lesson. You'll do the exit ticket, okay? And then you'll move on to your lesson reflection in Google Classroom. Class expectations, keep your video on, mic muted, you know that. Make sure you're showing your thinking in your work. Participate in your group in breakout rooms. Have appropriate conversations related to our math. Communicate any technology issues to me. Be respectful, responsible, and safe, and make sure you are completing your class jobs. As always, keep in mind the question, how does this pertain to your life? Why does this matter? Okay, that's going to be part of your reflection today. And let's get started. All right, here I'm just going to be reviewing some background knowledge and refreshing our skills when it comes to reading word problems that are representing real-life situations and creating tables and graphs based on those things. So it says Derek tells you that the number of 2-point shots he made is 5 more than the number of 3-point shots. So he makes some 2-point shots, he makes some 3-point shots, but there's 5 more of the 2-point shots. Okay? Write an equation representing the situation where x represents 2-point shots and y represents 3-point shots. So if I have y, the number of 3-point shots that he makes, he just makes 5 more of those than he does the 2-point shot. So this is the equation I came up with, okay? When looking at this equation, you can see that it's written in slope-intercept form, y equals mx plus b. And looking at this equation, you should notice that there is no number in front of my x, so it is an invisible coefficient of 1. So looking at this equation, my slope, if I were to graph it, would be a 1, and my y-intercept would be a 5. Now the second part here asks me to come up with combinations that actually fit the scenario. So the scenario is he always makes 5 more 2-point shots than 3-point shots. So I'm going to say here are my 2-point shots, here are my 3-point shots, x and y. So if I made one 3-point shot, he makes 5 more 2-point shots, so 5 more than that one. He would make 6 2-point shots. Choose another number 3. If he makes 3 3-point shots, he's going to make 5 more 2-point shots, so he would make 8, because I just add 5. So he makes 10 3-point shots, which is kind of crazy. He would make 15 2-point shots. So the reason being that I'm doing this is just to kind of get you used to understanding what this actually means in terms of the situation. All right? Now it does have me graphing the situation. I'm not going to graph it, but I am going to note that the m, or the slope, is 1 over 1, because it was a 1 right here. The rise is 1, the run is 1. And the y-intercept, where it crosses my y-axis, is at positive 5. Okay? And again, this was just building some background skills, or knowledge, and refreshing some skills before we get into our new learning today. Okay, so for example 1, we are starting with our new learning. I want you to just write down everything I write down and really try to absorb this information, keeping in mind this is the first time you're seeing it, so don't get overwhelmed. It says 2 cars drive from town A to town B at constant speeds. If they're constant speeds and they have a slope, right? They have a rate. The blue car travels 25 miles per hour, and the red car travels 60 miles per hour. The blue car leaves first, and the red car leaves 2.5 hours later. The distance between the two towns is 150 miles. So from what I just read, I know two things, or a couple things. I have two cars. They're driving at different speeds. One's only driving 25 miles an hour. One's driving 60 miles an hour. They don't leave at the same time, but they're going the same distance. They're both going 150 miles. They're traveling that far. But the blue car leaves 2.5 hours before the red car does. Okay? So the first thing I want to do is identify my x and y variables. So what are the things I'm dealing with here? What two concepts? I'm dealing with miles and hours. So when I think about miles and hours, I'm just underlining everything that says miles and hours here. I need to identify what is my x value, what is my y value. Remember that x is independent. It doesn't need anything to rely on. And we've talked about this many times before, but anytime you have time, that is your independent variable. So our x here is going to be our hours, because that is time. Our y variable is our dependent variable, and this relies on our x. And in this case, it's going to be our miles, because the amount of miles we travel depends on how many hours we're driving. Okay? So now I'm going to do part B. It says write an equation for the speed of the red car. So it says the red car travels 60 miles an hour. So I'm using these variables y and x. So y is my miles. So y is going to be 60 miles in 1 hour. So what I want to do here is just write down the rate of this car. Remember that the rate, or m, is y divided by x. So in this case, my y, my miles, is 60 miles. So it's going to be 60 over per hour. That just means per 1 hour. So m equals 60 over 1. That just means m equals 60. So that's my rate. So if I were to write this in y equals mx plus b, y equals mx. So this is my equation for my red car. Y equals 60x, because that's my rate. Okay? For my blue car, I'm going to be doing the same thing. Now, if I look at my blue car, 25 miles an hour. So again, I know that m equals y divided by x. My y is my miles, so there's 25 miles. So it's going to be 25 over my hours is my x. That is going to be 1, and 25 over 1 equals 25. So the equation for this blue car is y equals 25x. Okay? And again, this is pretty much just what we've been doing over the last couple of weeks. This is where our new learning comes in, part D. How will the extra 2.5 hours of driving affect the blue car's equation? So our blue car, this one right here, drives for an extra 2.5 hours because it leaves 2.5 hours before the red car. So if I'm thinking about my hours and I'm adding 2.5 hours, remember that this is my x. So I'm going to be adding 2.5 to this x. So my equation is going to change a little bit. It's going to say y equals 25, and instead of saying x, I'm going to be adding 2.5 hours to that x. Okay? So how did that affect my equation? Well, I just showed that there's an extra 2.5 hours, so I just added 2.5 to my hours. And if you want to, which I want you to do, you can distribute this. So 25 times x is 25x, and we have our plus sign, and then 25 times 2.5, if we do that in our calculator, we get 62.5. So this is how the equation is now going to look when we represent that extra 2.5 hours of driving. Okay. The last part of this question asks us to write a system of equations for the red car and the blue car. Now, this might just seem like a different language to you, but this is how you write a system of equations. First, you make this bracket that I've made off to the left, and we're representing the blue car and the red car. So the red car's equation didn't change from the beginning. It was y equals 60x. And the blue car's equation, after we changed it to represent those 2.5 extra hours, it became y equals 25x plus 62.5. Okay, so that would be our system for this example. One thing I want you to keep in mind is that this is your first example for today, so it is probably going to be confusing at first. All right? Just bear with me. We have a couple more examples to do. We're going to do some exercises, so get this down, and then we're kind of going to just continue to learn together, okay? All right, for example 2, it says Pia types at a constant rate of 3 pages every 15 minutes. Pia's rate is 1/5 of a page per minute. She typically begins work at 8 a.m. every day, but for some reason she started working 5 minutes earlier today. Now you notice, this is not a question. It's just a situation, and we want to just take the situation and represent it mathematically. That's what today's lesson is all about. Reading a real situation and using math to represent it. So the first thing we're going to do is identify our x and y variables. So we're talking about pages and minutes. Which one of these is independent, which means nothing affects it? Well, time. Time is always independent. So that is my x variable, which means this has to be my y variable. So x is our minutes, and y is our number of pages. This is old learning. You should be able to do this without my help, okay? Next, it says identify the equation that represents Pia's normal day of typing. So we're writing an equation in y equals mx form. Okay, remember, we could have a b, but it could be 0, and we just take that off. Now it says that we need to write this equation, so what we need to find is what was her rate. What's the rate that she typed at? Remember, we find m by doing y divided by x. So what was her y? Well, she did 3 pages, so this is going to be 3 divided by 15 minutes. That was her x, y divided by x. So 3/15 is her rate. We know that that can reduce, and this reduces to 1/5. And it did actually tell us that in our equation. We didn't have to do the math out, but I wanted to practice showing you. So her rate, or her m, is 1/5. And I'm just going to use that 1/5 to write my equation. So it becomes y equals 1/5 x, because that's my rate. And I don't have a b, so it can either just be plus 0 or plus nothing. Okay? From there, my next part asks me, how is the extra 5 minutes of work time going to affect her equation? So she has 5 extra minutes. Now, if you have extra of something, you're adding it. So I know I'm going to be adding 5. But what am I adding 5 to? My y or my x? My minutes or my pages? Does she have 5 extra minutes or 5 extra pages? Well, she has 5 extra minutes. So I'm going to be adding 5 to my minutes. So it's going to be adding 5 to my x, because x variable is our minutes. Okay, hopefully that makes sense to you. So D says, write an equation that represents what just happened, adding that extra 5 minutes to your x. So if she starts 5 minutes earlier, it's going to change her equation, because it's now going to say y equals 1/5. But now we have to add 5 to our x. So we take our x, we're adding 5 minutes. Okay? From there, I'm just going to distribute this 1/5. 1/5 times x is 1/5 x. And then 1/5 times 5, Well, 5 over 1. 1 times 5 is 5 over 5. 5 over 5 is the same as saying 1. So I've just changed my equation, and it now looks like this: y equals 1/5 x plus 1. Okay? That is the meaty part of our new learning today, is figuring out how our equation gets changed when our situation changes. And you'll see, what's the difference between these two equations? Well, when our situation changed and we had 5 extra minutes, instead of saying plus 0 at the end, because there's nothing being added to the end, it is now plus 1. The last step here is to create a system of equations comparing her normal workday and her early workday. So her normal workday was just y equals 1/5 x, and her early workday is y equals 1/5 x plus 1. So this is our system of equations here. Okay, I'll give you a second to get this written down, and then we're going to move on to our third example. All right, example number 3. Our situation is described here. It says Sandy and Charlie run at constant speeds. The distance between the school and the station is 2 miles. Sandy runs from their school to the train station in 15 minutes, and Charlie runs the same distance in 10 minutes. Charlie starts 4 minutes after Sandy left the school. So we want to take this situation and we want to represent it mathematically. The first thing we're going to do is identify our x and y variables. So the things we're talking about here are miles and minutes. Okay? Now, which one of those is independent? Time is always independent, so our x is our minutes, which leaves our y to be dependent, our miles. The amount of miles they run depends on how long, how many minutes they've been running. Okay? First thing I'm going to do is write an equation to represent Charlie's speed. So it says Charlie runs the same distance in 10 minutes. So I need to know what was the distance. What said they run from the station, which is 2 miles. So 2 miles in 10 minutes. I want to write his equation. So I want to do y divided by x. Well, his y, his number of miles was 2, and he did that. What was the time he did that in? 10. Can I reduce this 2/10? Yes, this reduces to 1/5. So this is Charlie's rate, 1/5. But now I need to write that into an equation. So I have y equals 1/5 x. So this is Charlie's equation. Okay. Now we're going to do the same thing, but instead of doing it for Charlie, we're going to do it for Sandy. So Sandy runs those 2 miles in 15 minutes. So for her, doing y divided by x, and remember that y was miles, so she runs 2 miles and x is minutes in 15 minutes. Now as I'm looking at this, I see that this fraction cannot be reduced. So her rate is 2 over 15, and we write that in equation as y equals 2/15 x. So I've just written Charlie's equation and Sandy's equation. Now the next thing that I'm going to do is figure out, how does this extra 4 minutes affect my equations? So it says Charlie starts 4 minutes after Sandy. So Sandy gets an extra 4 minutes. How is this extra 4 minutes going to affect the equation? Well, if you have extra time, you're adding time. So I'm adding 4 minutes. Am I adding that to my x or my y? Well, minutes is my x. So I'm adding 4 to my x. So for Sandy's equation, which was this right here, it is now going to be y equals 2/15. That doesn't change. And then we're taking the x and we're adding 4 minutes. All right? And we can simplify this by distributing. So we'll distribute 2/15 to the x, and we'll distribute 2/15 to the 4. So I'm going to do 2/15 times 4. So 2 times 4 is 8. 15 times 1 is 15. So this is her new equation representing that extra 4 minutes of running that she gets. All right? The last thing we're going to do is create our system. So we want to represent Sandy and Charlie's speed for this whole situation. So we want to include our extra minutes. So I need Charlie and Sandy. So Charlie's equation was the one in blue. We never changed that. That was y equals 1/5 x. And Sandy's, after we added on those extra 4 minutes, it changed a little bit. It says now y equals 2/15 x plus 8/15. And this is our final answer for our system of equations here. Please make sure you have all this down, and we're going to go into our lesson new learning and kind of talk about what we've learned so far today before you work on your exercises. All right, here's our new learning for today, and I'm just going to go over this. You do not have to write this down, just make sure you're listening, okay? So today we are looking at real life situations, and we're just writing them out mathematically. Specifically, the new part is down here. It is figuring out how does some situational change affect our equation, all right? So Randy and Craig ride their bikes at constant speeds. Randy takes 25 minutes to ride 4 miles, and Craig can bike 4 miles in 32 minutes. Our first step is to always identify x and y. X is always time, so in this case it's minutes, and y is whatever is left over. In this case it is miles. All right, we want to identify the equation that represents Randy's speed first. So I'm looking at wherever it talks about Randy, and it says 25 minutes, 4 miles. So I'm going to be doing, what is the rate for Randy? 25 minutes, 4 miles. So I need to do y divided by x. Well, y was our miles, so 4 miles. X was our minutes, 25 minutes. So this is our rate, and we just add that to our equation by saying y equals m, which we just did that, 425, or 4/25 x. So this is the equation that represents Randy's speed. All right. From there, we want to do the same thing. We want to write the equation that represents Craig's speed. So we're doing y divided by x for Craig. Craig can bike 4 miles in 32 minutes. So we have y over x. Y is our miles. So 4 miles in 32 minutes. So Craig's equation is 4/32x. Okay? But we have a loop thrown in our plan, right? It says that Randy gave Craig a 20-minute head start. So that changes things. We can't just keep the equations the exact same as they were. It has to change something. So how is this extra 20 minutes going to affect our equation? So just real quick, there is a typo here. It says, how will the extra 20 minutes of running affect Sandy's equation? This is supposed to say Craig's, because Craig gets a 20-minute head start. So looking at Craig's equation right here in blue, it's going to affect that. So what's going to change? Well, you get extra time, then we're going to be adding that time. You get 20 more minutes to run. Now, if we're doing 20 more minutes, then what variable are we adding that to, x or y? Well, x represents our minutes, so it's going to be x plus 20. And I'm going to show how that's represented in this equation right here. So instead of saying y equals 4/32 just x, it's now going to be x plus 20 because I'm doing 20 extra minutes. And I can distribute this to simplify my equation very simply. So 4/32 times x equals 4/32x. And then if I do 4 times 20, that is 80/32 times 1, that's 32. So you'll see that my equation has definitely changed from when we're just writing what Craig's original speed is versus what Craig can run when he gets a 20-minute head start. Okay. Last part of today's lesson is we are learning how to write a system. And we use this brackets, and then we write it down. So we're going to write Randy's speed first, and then we're going to write Craig. And we're writing this whole situation, so we are going to use the equation that we changed up. So we have Randy, which is in red, y equals 4 over 25x. And then Craig's is now y equals 4 over 32x plus 80 over 32. All right. And that is our new learning for today. We're about to get into some exercises, but before we get into some actual exercises with our group, we want to do some physical exercises to break up our day. So if you are the yogi for this class, please tell me in the chat what exercise you want us to do for 30 seconds to a minute before we get into our math practice. All right, here's your first exercise that I want you to do with your group. Efrain and Fernie are on a road trip. Each of them drives at a constant speed. Efrain is a safe driver and drives 45 miles per hour. Fernie is not such a safe driver and drives 70 miles per hour. They left from the same location, but Efrain left 3 hours before. So this is the change that's taking place in our equation, is this extra 3 hours. But don't worry about that now. Just go through and answer these questions one at a time. Identify your x and y variables. Write an equation for Efrain's speed. So I want you to find m here. And then write it into an equation. And then C, write an equation that represents Fernie's speed. Again, I want you to find m here. And then represent that in an equation. And then I want you to tell me, how does an extra amount of time, extra 3 minutes, affect Efrain's equation? And then lastly, I want you to write a system of equations here down below. I'm going to give you guys about 5 minutes to try this with your groups before we go over it together, okay? All right, the first thing you needed to do was identify your x and y variables. I do apologize, this says minutes, it should say hours. But our x is always time, so our x's are hours, and our y is our miles. You should have identified that with your groups. From there, part B, you need to write an equation for Efrain's speed, and we're writing this in y equals mx format. And we need to find m to do that. So m is going to be y divided by x, miles divided by minutes. For Efrain, I have 45 miles, miles divided by hours. I have 45 miles per 1 hour, so it's going to be 45 over 1. And what does that reduce to? 45. So this is my rate. And I write that in my equation by just saying y equals 45x. And this is my equation for Efrain's speed. We're going to do the same thing for Fernie. Fernie, however, drives a little bit faster, a lot faster, 70 miles per hour. So our equation is going to be 70 miles divided by 1 hour, which means our m comes out to equal 70. And our equation looks like this, y equals 70x. All right? But we know that something extra happened in this equation. Efrain left 3 hours before Fernie, so we have to represent that with our math somehow in our equation for Efrain. So the extra 3 hours of driving affects Efrain's equation. So we're doing extra time, so it's going to be added. And what is it added to, our x or our y? Well, hours is our x, so it's going to be added to our x. Okay? So my new equation for Efrain becomes y equals 70x plus 3, because I have 3 extra hours. Okay? And from there, you needed to distribute this to get your equation simplified in y equals mx format, mx plus b format. So 70 times x is 70x, and 70 times 3 is 210. So this is the new equation for Efrain when we factor in those extra 3 hours. The last thing we're going to do is write our system out. So for Fernie, we had y equals 45x. And for Efrain, we had y equals 70x plus 210. And what that means is that this person's probably going to go 210 extra miles before Fernie even leaves. Or Fernie even leaves. And please check your work with my work before we move to exercise number 2. All right, exercise number 2, here's your situation. Jessica and Carl run at constant speeds. Jessica can run 3 miles in 24 minutes. Carl can run 2 miles in 14 minutes. They decide to race each other, but as soon as the race begins, Carl trips and takes 2 minutes to recover. So you're going to factor that into your equation. The first thing I want you to do is identify your x and y variables. We're doing miles and minutes, so identify which is which. The next thing I want you to do is identify the equation that represents Jessica's speed. So we need to find y divided by x for her. And then write an equation with that speed. And then we're going to do the same thing for Carl. From there, we want to figure out how do these extra 2 minutes of running affect Jessica's equation, because she gets the extra 2 minutes. And then lastly, down below, I want you to write your system of equations. All right, take a couple minutes to do this with your breakout group before we go over it. All right, x should have been identified as your independent variable, which is time. So in this case, it is minutes. And y would be your miles. We want to write our equations for these lines in y equals mx form. In order to do that, we have to find our m. So for Jessica, we're doing y divided by x, miles divided by minutes. She runs 3 miles in 24 minutes. And this reduces because both are divisible by 3 to 1/8. So her equation is going to be y equals 1/8 x. All right, moving forward, we're going to do the same thing for Carl. Y divided by x, miles divided by minutes, 2 miles, 14 minutes, and this also reduces to 1/7. So this equation is y equals 1/7 x. Okay. Now, in this case, Carl trips, and he takes 2 minutes to recover. So it turns out that Jessica gets an extra 2 minutes to run without him doing anything. So extra 2 minutes, we're going to be adding 2 to our x, and we're going to make sure that this is for Jessica's equation. So Jessica's equation was this first one we did, the red one. So I'm now going to write out what's going to change to her equation. We have 1/8, and we're just adding 2 to our x. I'm going to distribute this and solve it to see what it comes out to be. 1/8 x plus, well, 1 times 2 is 2. 1 times 8 is 8. And that could be reduced, but I'm not even going to bother with it right now. So I have my 2 equations now. I have one for Jessica, and I have one for Carl. Jessica's new equation was affected, so this is the new equation for Jessica. It is y equals 1/8 x plus 2/8. And Carl's equation was this original blue one right here, y equals 1/7 x. Check your work with my work, and we're going to move on to exercise 3, which you will do on your own for some practice. All right, for this exercise, you're going to be doing it on your own. It says Jeremy and Gerardo run at constant speeds. Jeremy can run 1 mile in 8 minutes, and Gerardo can run 3 miles in 33 minutes. Jeremy started running 10 minutes after Gerardo, so Gerardo ends up getting an extra 10 minutes to run. First step, as always, identify your x and y. Remember that x represents time. Second step, you're going to write your equation y equals mx form, but you need to find out what is your m equal by doing y divided by x. That is the same for C. Writing your equation y equals mx form, find your m by doing y divided by x. Explain to me how this extra 10 minutes affects Gerardo's equation. And then down below, write your system of equations. Take a couple minutes to do this before we go over. All right, you should have identified that x represents minutes and y represents miles. For Jeremy, we're doing y divided by x, miles divided by minutes. So we have 1 mile, 8 minutes. this means that Jeremy's equation is going to be y equals 1/8 x. And we're going to do the same thing for Gerardo's. Gerardo's is y divided by x, 3 miles in 33 minutes. Well, this reduces to 1/11. So this becomes y equals 1/11 x. Okay, our new learning today, how does this situation affect our equations? So there's going to be an extra 10 minutes. So we're adding 10 to our x for Gerardo's equation, and the reason for that is that he gets 10 more minutes to run because Jeremy started running 10 minutes after him. So Gerardo's equation was the one we wrote in C, so it's going to affect this equation right here. So it changes to show that we're adding 10 minutes to our x. I can distribute this like you should have done. This becomes 1/11 x plus, when I do my multiplication here, 10 times 1 is 10, 11 times 1 is 11. So this is my new equation for him. So when I go ahead and write these equations out, I have Jeremy. And that equation never changed. It was just y equals 1/8 x. And then I have Gerardo. And this is the one that got changed because of the extra time he gets to run. It's 1/11 x plus 10/11. And that is our system. Okay? Check your work with my work. And we're going to go ahead and close out this lesson before we do our exit ticket. All right, to close out this lesson today, I want to just reiterate that we learn math because it is all around us. So situational problems like the ones we saw today may not actually come up in your life, but some sort of situational problem where you can use math absolutely will. All right? Outside of that, you need to learn this math to move on to high school, right? Your math will build in high school to prepare you for graduation and college and careers. So you have to make sure you understand this so that you can move forward in life to those things. It applies in many different ways to your life, even if it's not in the specific career that you choose. So today's lesson was all about how changes in our situations directly affect how our math equations change and how we write them. And we can just show exactly the changes happening in our situations with mathematical work. All right. So make sure you can do these things before moving on to the exit ticket. Make sure you are good with identifying your x and y variables. Make sure you can write an equation by finding your m, your rate. Make sure you can understand how the way a situation changes will affect your equation, right? In this case, every time we were just adding to our x. And then make sure that you can change your equation using what happened in your situation. What changed in your situation needs to change your equation, all right? And if you feel confident with this, please move on to the exit ticket. If you do not, please go back and rewatch some of these examples. Maybe seeing them a second time or even third time will give you a new perspective and help you out a bit. For your exit ticket today, it is almost exactly like everything we have done, just a different situation. It says Darnell and Hector ride their bikes at constant speeds. Darnell can ride the 8 miles to Hector's house in 32 minutes. And Hector can ride the same distance, so 8 miles, to Darnell's house in 24 minutes. 5 minutes after Darnell leaves, Hector realizes that Darnell left his phone, and Hector rides to catch up. So this is our situation. First thing you need to do is identify your x and y variables. The second thing that you're going to do is write the equation for each of these people. What you have to do to write these equations is identify the rate. So the first one's for Darnell, so go find Darnell's rate based on the equation. The second one is for Hector. Go find Hector's rate based on the equation, and remember that m is just y divided by x. All right. The third question asks you to please identify how is the extra 5 minutes going to affect Darnell's equation. So please describe to me there, how is that going to affect it mathematically, and show me how it affects it mathematically. And then the last part is to please write a system of equations representing Hector and our Darnell's speed. Remember that you have to change Darnell's equation to represent that extra 5 minutes. Okay, take your time on this. Show your work. If you're getting stuck, please reference the different examples and exercises we did together. Please message me in the chat or through ClassKick. And when you finish this, as always, go complete your lesson reflection.